Hello and welcome to our discussion on periodic trends. Periodic trends goes hand in hand with periodic law that we got from Mendeleev, which says that if you order the periodic table by atomic number, then all these patterns start to appear. And periodic trends kind of explores those patterns. So I'm going to break the periodic table down into groups and also into periods, and we'll look at the patterns that appear in each of those situations. A couple of things that we need to talk about are nuclear charge and electron shielding. We'll get to that in just a second. Nuclear charge is talking about the charge inside of a nucleus. The charge in a nucleus is based off of the protons, which means that it's a positive charge. So it's what pulls in the electrons, because electrons are negatively charged. And we all know that opposite charges attract. Okay? Electron shielding is talking about the increase of energy levels adds a new ring of electrons as each time you move down a row on the periodic table. And that means that layers of electrons are sitting next to each other and they're all negatively charged, which means they repel each other. So they kind of push away from each other a little bit. So in a group, as you move down the periodic table, the orbitals are going to get larger because you're adding more and more electrons and they keep pushing away from each other each time you add more. Electrons get further away from the nucleus because every time you add a new energy level, you increase the distance away from the nucleus. And then valence electrons, those are the ones in the outermost energy level, are less tightly bound because they are further away from the nucleus where the protons are. So the protons can't pull on those outer electrons as much as they can pull on electrons that are closer to them. And hopefully that makes sense to you. Alright, now let's talk about within a period. So within a period, we have nuclear charge. Okay, within a group, we had electron shielding. Remember, groups go up and down, periods go side to side. So just a second ago when we were talking about groups, we focused on electron shielding. And now that we're in a period, we're going to focus on nuclear charge, or that positive charge. Okay, so electrons get pulled in closer to the nucleus because as we move this way on the periodic table, the atomic number increases, and that atomic number stands for the number of protons that you have. So the more protons you have, the more positive charge you have, which means you're able to pull on the electrons, the negative charge, even more. So it's like getting a stronger and stronger magnet. Valence electrons would be more tightly held because there's more protons pulling on them. So let's take a quick example here. Let's say that we're in the first energy level here, okay? Hydrogen has one proton and it's got one electron, okay? There are no extra rings in the hydrogen atom. There's just one. The helium atom has two protons and two electrons. Let's draw a picture of hydrogen versus helium. Okay. So here I'm going to say this letter H is the nucleus, and so we know that there's one proton there, and here we have one electron. Now let's draw helium. Okay, so inside of hydrogen, the nucleus, we have one proton. Okay, and inside helium, we have two protons. Alright, notice that the electrons are the same distance away in both of these atoms. This electron is exactly the same distance away from the nucleus as this electron is. So the one proton in the nucleus of the hydrogen atom can pull on this electron, and they kind of I don't know, cancel each other out a little bit, you might say. But here, these two protons are pulling on these two electrons, and these two electrons are the same distance away as this one electron is. So they can actually be pulled in a little bit closer to the nucleus than what hydrogen's electron can be, because now there's two protons pulling on them. Okay, so let's talk a little bit more about electron shielding, alright? The electrons in the energy levels between the nucleus and the valence, or outer energy level, are called shielding electrons because they shield the valence electrons from the force of attraction exerted by the nucleus, or the protons within the nucleus. This is because electrons repel each other because of like charges, okay? So if we're looking here at this ring here, we've got our nucleus in the center, we've got the first energy level, we've got the second energy level, and we've got the third energy level, which would be the valence energy level. Okay, well, there are 11 protons inside the nucleus, and we have 11 electrons circling it. This very most outer electron is not feeling the full force of the 11 protons in the nucleus pulling on it, because these 10 electrons here that are between the nucleus and the valence electron block some of that charge. They cancel some of it out before that positive charge makes it out to that outermost electron. So this electron is not very strongly attracted to the protons in the nucleus here, because these guys are pushing this electron away. These are all negative charges in here, and this electron is a negative charge, so they repel. The outermost electron pushes in on these electrons, and all of these electrons, as they spin around, push out on that outermost electron. So this guy actually gets pushed out away a little bit, and these guys here get pushed in a little bit closer because they don't like each other. Alright? Now let's talk about effective nuclear charge. We said a little while ago that nuclear charge refers to the charge within a nucleus. The charge inside the nucleus is protons, and therefore we're talking about the net positive charge experienced by an electron in an atom. The term effective here is used because shielding, the electron shielding, stops some of the electrons from feeling the full force of the nucleus. Okay, so these electrons that are outside have no effect on the nuclear charge for an electron that is closer in. Notice that the electron of interest here is closer into the nucleus than these electrons out here. So they can't shield this electron because they're not between this electron and the nucleus. Okay? Now, these electrons here in the green area, those can shield the electron that we care about from some of the positive charge of the nucleus because they're between the electron we care about and the nucleus. Alright? So let's start talking about how we apply effective nuclear charge and electron shielding to our periodic trends. There are 3 periodic trends you're going to have to know. Okay? The first periodic trend, let me move this over a little bit. The first periodic trend is going to be atomic radius. Okay, that's the first one we care about. So, let's define atomic radius before we go any further. In chemistry, let's imagine that we're looking at our cloud model, because this is really how an atom actually looks. How can I be sure that these electrons out here on the edge are as far out as they can get? I mean, here's another electron that's pretty far out, but could it go further? I don't know really what the edge of the electron is. not the electron. I don't know what the edge of the orbital is. So I don't really know how far out these electrons can go. So when we're talking about atomic radius, that makes it a little difficult. Normally, when we do a definition of a radius, we start at the nucleus and we go out to the edge of the circle, and that's the radius. But since we don't know what the edge of the circle is for an atom, because we really don't know how far out those electrons can get, that makes defining the radius of the atom a little bit trickier. So here's what we actually do. We actually say, okay, well, what if we bonded two atoms together? Okay, these are supposed to be touching, but I couldn't, for some reason, make that happen. So we've got two atoms here. We've got their nuclei in the center, and they're bonding. Okay, so we have a force of attraction between the electrons and the protons inside the nucleus. The actual definition for atomic radius is that it is 1/2 of the distance between two nuclei of a bonded pair of atoms. Okay, so it's 1/2 the distance between nuclei of bonded atoms. Okay, so that's actually how it's really defined, but that's kind of difficult for us to imagine. So I want you to know that that's the real definition that you'll see in textbooks and things, but we're going to just use the traditional way of thinking about radius to help us with our atomic trends, our periodic trends. So the atomic radii, that just means the radius in its plural form, so of all of the atoms. The atomic radius will increase if you increase electron shielding. Okay? Now remember, electron shielding happens in a group. Groups are up and down. So if we increase electron shielding, then the atomic radius is going to increase. That's because as we move down the periodic table, we keep adding energy levels. So we start with 1, and then 2, and then 3, and then 4, and so on and so forth. And when we do that, what do you notice about the atomic radius in each of these cases? Hopefully you notice that the atomic radius keeps getting larger and larger and larger as we add these different energy levels. So electron shielding increases the number of energy levels, which increases the distance away from the nucleus that the electrons are. So the atomic radius goes up. The atomic radius will go down if you increase the nuclear charge. Remember, nuclear charge happens left to right on the periodic table. So if you go left to right on the periodic table, you're going to increase the number of protons. If you do that, then those protons can pull in on those electrons even more, which makes the energy levels get smaller. And so that shrinks the atomic radius. So here's what that atomic radius trend would look like on the periodic table. As we increase the electron shielding as we go down the periodic table, we will increase the atomic radius because we're adding energy levels. As we move this way on the periodic table, we are getting less and less protons. Notice how the atomic number is dropping. And because we are having less and less protons, that means that they're not able to pull on the electrons as much, which means the electrons can get further away. So the atomic radius will increase. Okay, let's talk about cations and anions. I don't think that we've mentioned these so far in the course, so I'm going to quickly talk about those. Here's a bit of vocabulary to kind of help introduce that idea. An ion is an atom or a group of bonded atoms that have a positive or negative charge. So for us, anytime that I talk about ions, our definition is going to be that it is a charged particle. Okay, and that means that it can be positive or negative. Okay? If it's a positive ion, meaning that it is positively charged, then the name we give it is cation. So a cation is just a positively charged particle. And a negatively charged particle, we give the name anion. So that's just a negatively charged particle. Now, I kind of try and remember them like cation has a plus sign in it, and that makes me think positive, and anion has an N in it, and that makes me think negative. So, back here at cations. Cations are going to have a smaller radius than their neutral counterparts. Here's what we mean by that. Let's say that we've got calcium, and we've got a calcium cation. Okay? The reason that the ion here is going to have a smaller radius than the actual element itself is because it's got this positive charge. That means that it's lost 2 electrons. Okay? You cannot lose protons and still be the same element. Notice, calcium has 20 as its atomic number. That atomic number stands for the number of protons it has. If it didn't have 20 protons, if it had 19 protons, it's not calcium anymore, it's potassium. So you can never change the number of protons an element has and still be talking about the same element. You can, however, change the number of electrons that it has. So if you want to change the charge of an element, you don't do it by adding or subtracting protons, you do it by adding or subtracting electrons. Okay? Now remember, electrons are negative, so if you lose 2 negative things, then you're going to become more positive. So the reason that this has a plus 2 charge is because it lost 2 electrons. Alright? So let's say I'm going to talk about hydrogen, and I'm going to talk about the hydrogen cation. Well, this hydrogen has 1 electron, and it's in the first energy level. This hydrogen has no electrons because it's lost that only electron that it had. Okay? So what did that do to the atomic radius then? If there's no electrons there, then the distance from the nucleus to the valence electron has shrunk by a lot because there's not even an electron there anymore. Okay? The same thing could be said for any of the elements. If you start losing electrons, then you start losing these energy levels, and then that means that the energy levels are going to get closer to the nucleus. So cations are always going to have smaller radii than their normal atoms. Anions are going to have larger radii than their normal atoms because we're adding more electrons. And if you start adding more electrons, you're eventually going to have to start adding energy levels, which will increase the distance from the nucleus. Okay, so let's use oxygen as an example. Alright, oxygen has 8 protons in the nucleus. Okay, so we've got 2 electrons, and then we've got the second energy level. We've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is going to be a normal oxygen atom. Okay, well now we're going to do the oxygen anion. Okay, let me just write down here that that's just regular oxygen. And over here we're going to do the oxygen anion. That means right here that we have 2 extra electrons because it's got a -2 charge. We have added 2 negative things to our oxygen. Alright, so it's still got 8 protons because you can never change the number of protons and still be talking about the same element. And it's still got these 2 electrons here, and it's still got these electrons here. But now we're going to add 2 more electrons. Okay? And because we've added these 2 extra electrons here, we've actually filled up this energy level. We've made it complete, if you will. And so the next thing, if we started adding even more electrons, we would have to add a whole nother energy level to this. That is going to increase the radius, the atomic radius. So anions are going to always have a larger radius than their neutral atoms do. Also, because we've added these extra electrons here, the number of electrons are actually more than the number of protons right now, which means that these 8 protons cannot pull on these 10 electrons very hard, and so these electrons are free to kind of move away from the nucleus a little bit because they're stronger than the pull of these protons. Here, the number of electrons perfectly match the number of protons, so they're kind of evenly balanced and they're stuck here. Over on this side, the electrons are winning the game of tug-of-war, if you will, and that allows them to get further away from the nucleus. So here we kind of have a pictorial representation of the sizes of the atoms as you move across the periodic table. So we get larger as we move in this direction, just like our other diagram showed you. And so the biggest elements are going to be down here in this bottom left-hand corner. Okay, so you get bigger as you go down in the groups, and the reason for that is because you're adding extra layers of electrons. We do not include noble gases in that because they don't really react with anything. And from lithium to fluorine, this is just an example, from lithium to fluorine, they're all in the second energy level. I've actually just taken the second row of the periodic table and pulled it out here. Okay, they're all shielded. All of the electrons that are in that second energy level there are shielded by the electrons in the first energy level that came before it. But as we move across this periodic table, we are increasing the number of protons each time we move across one more element. And because of that, those protons are pulling on those electrons the same amount, or excuse me, in increasing amounts, which means that the electrons move closer and closer to the nucleus. So the atomic radius shrinks as you move from left to right on the periodic table. Okay, back to our vocab real quick. We already talked about what an ion is. Now let's talk about ionization. Anything you do to an atom that causes it to make an ion is going to be ionization. So if you make it become positive or you make it become negatively charged, you have ionized the atom. An oxidation number. An oxidation number is the charge that results when an atom is ionized, or when it loses or gains electrons, which, by the way, that is how you ionize something, losing or gaining electrons. Okay, so whatever charge you get when you ionize an atom, that's the atom's oxidation number. Metals will tend to lose their electrons and become positive. Okay? Nonmetals tend to gain their electrons and become negative. Okay? Metals are located on the left-hand side of the periodic table. And when we say left-hand side, we use this stair-step line here to separate the sides of the periodic table. So everything to the left of that line is a metal, and everything to the right of that line is a non-metal. So all of this stuff over here loses electrons and becomes positive, and all of this stuff right here gains electrons and becomes negative. We know that the valence energy level is the outermost energy level of an atom, and valence electrons are electrons that are in the outermost energy level. So they're furthest away from the nucleus, and they are the ones that are able to be lost or gained or shared in a bond. Okay, which brings us to our second periodic trend. First, ionization potential, also sometimes called ionization energy. Okay, so ionization energy is the amount of energy that it requires to remove an electron from an atom, molecule, or ion. So, if you move down a group, the ionization energy is going to decrease because there's more electron shielding. Okay, so let's think about this. If we put an atom over here, and I start adding these little energy levels to it, let's put in some electrons. Alright, this outermost electron here, it really can't feel the full force of the nucleus because it's got all these shielding electrons in between. Remember, these shielding electrons kind of take some of the brunt of the nucleus, and this guy out here doesn't have to feel it very much. So what if you were another atom, so some other atom comes along, and that atom needs an electron. Okay, so let's say that this atom over here is almost complete, and it just needs one more electron right there in order to be happy. Okay, well, this electron here is not really that attracted to this nucleus. The nucleus is not being able to hold on to its electron very well. So this nucleus comes along, notices that, and it steals that electron. And so that electron moves right up here. Well, we have to decide, was it easy for this nucleus to do that, or was it difficult? Okay, in this case it was pretty easy to do that. So the ionization energy of this electron is low because it's easy to take it away. And the reason for that is because of all this electron shielding we have right here. Alright, now if you move across a row from left to right, the ionization energy is going to increase because you have an increased amount of nuclear charge. Alright, what if we bumped up the number of protons in the nucleus? If we do that, if we have a whole bunch more protons in the nucleus all of a sudden, it's going to pull all of its electrons in closer to it, which means it's going to be way more difficult for some other atom to come along and steal an electron, because that electron is going to be so much more tightly held onto by the nucleus. So the ionization energy will increase in that case, meaning it's more difficult to steal that electron. So you need to be able to relate every periodic trend to nuclear charge and electron shielding. That's how you do this. That's how you do periodic trends. If you can define the periodic trend, if you can define what ionization energy is and atomic radius is, and then you can relate it to the nuclear charge and the electron shielding, then it makes everything much more simple. So let's look at the periodic table with this trend on it. So here's what the trend for decreasing ionization energy looks like. The more energy levels you add, the more electron shielding you have, which means that the electrons are less tightly bound by the nucleus, which means it's way easier to take them away. So the ionization energy decreases. It's not that difficult to ionize the element. Okay, on this one, if we move from right to left, the nuclear charge decreases because we have less and less protons. And if you have less and less protons, that means that they are less and less able to hold on to their electrons, which means it's way easier to steal an electron. So again, the ionization energy decreases. If you are asked for the trend for increasing ionization energy, you would just do the reverse of this. You would draw your arrows up and then from left to right. And so we've talked about electron shielding here and how it affects our ionization energy. Okay, the third periodic trend we're going to have is electronegativity. Okay, so electronegativity is the ability of an atom to attract electrons to itself. Okay, so how well can you attract electrons to yourself? Now let's think about that. How would you attract electrons? Well, if electrons are negatively charged and you intend to attract them to you, then what do you need to be or have a lot of? Positive. You would need to have a lot of positive charge in order to attract that negative charge. Okay? So electronegativity decreases down a group because of increased electron shielding, and it increases as you move from left to right because of increasing nuclear charge. Let's talk about that a little more. If you have increased electron shielding, meaning that you have added a whole bunch of energy levels and you have filled those energy levels with your electrons, then that means that you've got a whole bunch of electrons and possibly not a whole lot of protons. And if that's the case, if I've got all these electrons on my energy levels and then some other atom comes along, so let me put some other atom here, some other atom comes along with some electrons on it, are these electrons on this atom going to want to be near this atom over here? No, because this one is filled up with electrons. So can this atom here attract new electrons to itself? Not very well, because the nucleus here where the positive charge is, it's got all these electrons in between it and the electron that it wants to steal. That means that it's not going to be able to do a very good job of taking that electron. So the electronegativity is going to decrease for this atom. It cannot do a good job of stealing that electron right there, or attracting that electron to itself. Okay? Now, increasing nuclear charge. Remember, nuclear charge is the charge inside the nucleus, which is the protons, which is positive charge. Okay? Well, if we move from left to right on the periodic table, then we are going to increase the atomic number. Okay? So, moving from left to right, the atomic number increases, which means that the positive charge increases. And remember, the more positive charge you have, the more electronegative you are, because you can attract electrons, negatively charged particles, to yourself. So as we move from left to right, that means that the electronegativity is going to increase because you can attract electrons more easily. Okay, so here's the trend for decreasing electronegativity. As we move down the group, we have more electron shielding, which means we are not going to be able to attract very many electrons to us because the nucleus is being shielded, and that's where all the positive charge is. And then if we move from right to left, we have decreasing electronegativity because there are fewer and fewer protons. That means less positive charge to attract those electrons with. If you need the trend for increasing electronegativity, you just flip the arrows and draw up and from left to right. So how do you keep all this straight in your mind? Here's the steps. Step 1, you need to define the periodic trend that they are asking you for. So if they are talking about atomic radius, you need to actually define that for yourself so you know what they mean. It's the distance from the nucleus to the valence energy level. Okay? Step 2, you need to relate that trend to the electron shielding in a group. So here's an example. The more shielding that you have, the more energy levels there are, which increases the distance from the nucleus. Okay? And we know that shielding increases down a group. Okay? Always remember that shielding increases as you go down a group, and then the nuclear charge we'll talk about in just a second in step 3. Step 3, relate the trend to nuclear charge across a period. So here's the example. As you move from left to right, the number of protons increases, which means the electrons can be pulled in closer to the nucleus. This decreases the distance between the nucleus and the valence energy level. Okay, and so we know that the nuclear charge increases from left to right. Okay, so what we just said here is since the distance decreases, that means the atomic radius has to decrease if you move this direction. Over here, we said that if you move this direction, there's more shielding, which means that we increase the distance. So you increase the atomic radius in this direction. So now we can apply that to a problem. Alright, so let's give ourselves a problem to play with here. In each of the following pairs, circle the species. A lot of times you'll start seeing species pop up in this course, and they're just talking about the chemical or the atom. So circle the species with the larger atomic radius. So here's the problem. They want larger atomic radius. So we have to come up with the trend for that. We know that the atomic radius, by definition, is the distance from the nucleus to the valence electrons. We know that if we move down a group, we increase electron shielding, which means we add more energy levels, which means the electrons get further away from the nucleus. So, as we go down, we are going to increase the atomic radius. Okay? We know that if we move from left to right, the number of protons increases, which means they can pull on the electrons harder, which means the electrons will move in closer, and that will shrink the radius. Well, we don't want it to shrink, we want it to get bigger, so the reverse must be true. If we move from right to left, then we have fewer protons pulling on the electrons, which means the electrons can get further away. So we just went through our 3 steps. We defined the trend, then we related it to electron shielding, then we related it to nuclear charge, the number of protons, and now we can apply it to our problem over here. So between magnesium and barium, we want to apply this trend. Alright, so here's magnesium and here is barium. Alright, it looks like they're both in the same column, so all we're going to have to worry about is the up and down. We want the larger radius, and we know that as you move down, you get larger. So which one, magnesium or barium, will have the larger radius? Okay, barium. Alright, now sulfur or the sulfur anion. Remember, anions always have larger radii than their neutral counterparts because we've had to add extra electrons, which means that the energy level got bigger. So the anion wins. Okay, now between copper and the copper cation. Well, remember, the cation is always smaller than the neutral counterpart. So that means the neutral counterpart must be larger. Okay, so now we have helium versus the hydrogen anion. Let's talk about that real quick. That's a little bit different situation. Here we have helium and it's got 2 electrons in the first energy level and it's got 2 protons in the nucleus. Okay, then here we have hydrogen with 1 electron in the first energy level and it's got 1 proton in the nucleus, and now we need to make this the anion, so we add 1 more electron. Okay, so these two things have the same number of electrons, they have the same number of energy levels, but what's different is the number of protons that they have. Helium has 2 protons pulling on these 2 electrons, which means that they're going to be pulled in and kind of cancel each other out. Alright? But hydrogen only has 1 proton pulling on 2 electrons. That means that this 1 proton can only kind of cancel out one of those electrons. The other electron is going to be able to not have any pull from that proton on it, so to speak. So that means that these electrons are going to be able to get further away from the nucleus than these electrons are because there's less nuclear charge pulling on them. So that means this one's going to have the larger atomic radius. Okay, last one, sodium versus chlorine. Okay, well, here is sodium and here is chlorine. So it looks like they're both in the same row as each other, so we're only going to be concerned about the nuclear charge. It looks like sodium is further to the left than chlorine is, so sodium is going to be larger. Okay, so hopefully that made sense to you and you can apply those 4 steps to solve any of these periodic trend problems that you may run into. See if you can solve these problems on your own using the 4 steps we talked about earlier. Define the trend, so you'll need to know what ionization energy is. Okay, then apply the electron shielding to the trend and apply the nuclear charge to the trend, and then use that information to figure the problem out. Okay, take a little bit, take a couple seconds and figure that out, and we'll come back and see what you came up with. Alright, here's what I've come up with. I did the trends here for increasing ionization energy, increasing atomic radius, and increasing electronegativity, because that's what the first 3 things were. So the highest first ionization energy, okay, meaning how much effort it would require to remove the first electron from an element, okay? Well, if you have a lot of nuclear charge, that means you've got a lot of protons, which means it's going to be more difficult to take an electron away from that element. Also, if you've got not very much electron shielding, meaning you don't have a bunch of energy levels, then all of your electrons are closer to your protons. So again, it's going to be more difficult for you to take an electron away from that element. So we've got carbon, we've got nitrogen, and we've got silicon. Okay, so we need to be as high up as possible. That rules out silicon and makes it between carbon and nitrogen. And you need to be further to the right. And so that means nitrogen's the winner. Okay. Then we have the larger radius. Okay. Well, we said that the anion is always larger than its neutral counterpart. So that means that the neutral chlorine is counted out, and now it's between the chlorine anion and the sulfur anion. Okay? And whichever one is further to the left wins, because that's going to be the larger radius. So that means sulfur anion is going to win. So there you go. Then the higher electronegativity. Alright? The the less electron shielding you have means that the electrons of another element are going to be able to be drawn into you because they're not being shielded away from your nucleus. And the more charge you have, the more you're going to be able to attract electrons from another element to you. So we need to have an element that's as high up as possible and as far to the right as possible. So let's see, it's between arsenic and tin and sulfur. So the highest one up is sulfur, and the furthest one to the right is sulfur. So sulfur wins. Okay, now the smallest atom. Well, this is the trend for the largest radius, so if we want the trend for the smallest radius, we just have to flip it. Okay, so we would do this as our trend for decreasing atomic radius. Alright, so we have sodium, lithium, and beryllium as our players. There's sodium, there's lithium, there's beryllium. We need it to be the highest one up, so that counts out sodium, and it needs to be the furthest one to the right. That means beryllium's the winner. Okay, and then we need the lowest first ionization energy. Up here we have the highest first ionization energy, so we just need to flip it. Okay, so the players are potassium, sodium, and calcium. We need to go as far down as possible, so that rules out sodium. And then it's between potassium and calcium, and we need the one furthest to the left, which means potassium is the winner. Okay, so I hope that you are able now to go through, come up with the trends. You need to practice learning the definitions and then relating electron shielding and effective nuclear charge to the definition so that you can come up with the trend for anything they ask you about, increasing ionization energy or decreasing, whichever way they ask you for it. Okay? Thank you so much for learning with me today, and I will see you next time.